I have to say a few words about you. David is a very good friend. He's one of my Canadian friends. ASHRAE, apart from all the knowledge that dissipates, it makes great personal relationships. And a few words before he starts. It's an honor to have you with us, David. David has 42. Thank you. Has 42 years of HVAC industry experience, including engineering, sales, design, project management, selection, installation, and validation of biopharmaceutical process and facility equipment, preparation and execution of installation and operation qualifications, IQ and OQ, presentation of information to regulatory authorities during inspections, creation and maintenance of preventive maintenance and calibration systems, management of cleanroom construction projects globally, setting up HVAC cleanroom standards, providing global synergies. We need to bring David to Greece at some point to have a physical presentation.
And thank you very much for this opportunity. It's unique, and Canada is a totally different climate than Greece. So anyways, we'll give it a shot here. And again, thank you very much for this opportunity. This Vivarium is a current project that we're in design, and the pharmaceutical lab is one that's been completed last year, and we're just finishing up. Both of these projects are university projects. Let's see. A little bit about Canada. Canada's the second largest country in the world, but only 38 million people. It's also the second coldest country in the world. It's about 10 million square kilometers. So it's a big country, and most of the people live down towards the United States, and Calgary is sitting right here where this arrow is in Alberta. So this is the city that I live in. I was born and raised. I did disappear for a few years, living in a couple of other cities in Calgary. But our design conditions are totally different than Greece. Our dry bulb in the winter is minus 30 degrees Celsius. In the summer, it's plus 30. Our wet bulb in the winter is 4.8, minus 4.8, and in the summer is 19.3 degrees Celsius. The city is about 1,000 meters above sea level, and we have 1.5 million people. Alberta province is 4.5 million people, and the capital is Edmonton, and we are at 825,000 square kilometers is our province. Alberta is an oil and gas rich province, so to make it net neutral is sometimes a little difficult. And our primary electricity is coal and natural gas. Currently in Calgary, we have about 6,000 hours a year of heating, 15,000 hours a year of cooling, and 1,200 hours, sorry, 1,500 hours of cooling and 1,200 hours of free cooling. This is just to give you a little distance how far apart we are flying, 9,000, and we're roughly 8 hours behind you. So it's showing up close to noon for me, and you guys are a little later than in the evening. Just to give an example, Canada is about 5,500 kilometers wide, almost half the distance to Greece. Now this is the Vivarium lab that we're kind of currently in design. We've been in design with this in the University of Calgary now for probably a 3 years off and on project. So there's several air handling units. Well, let me start at the bottom, would probably be better. So it's a campus that has a district heating system, and it has hot water pressurized systems. So basically there's two 32,000 MVH heat exchangers at 2,700 kilopascals at 204 degrees C coming in to the building from their district heating. And the cooling in the university is kind of rare. They actually tap into the city river that flows through the river, and that's their cooling loop. But because this building is a new building and it's going to be on the edge of the campus, we do have a 400-ton chiller here just for extra cooling if needed. And the Vivarium lab, which is going to be in this area, is basically going to be housing 3,000 mice, 1,000 rats, 100 rabbits, and the water demand for this building is about 3,200 meters cubed. And the Vivarium is going to be roughly 15 air changes. And then this here down here is an aquarium area that we're going to be using, and then the water and neutralizing systems. For the labs, like Demetrius just presented, we use Venturi valves to control pressurization, and we offset it if it's negative. So the supply and the returns will both have valves coming in and out, and we'll offset them about 10%. And I'll get more into detail the air handling units too, but because they have energy recovery. Fume hood exhaust with energy reclaim in it to go out, so we get a high plume, so the smells, because from the animal you get a lot of ammonia smells from the urine. This is an adiabatic fluid cooler. There will be 400 tons tied into this chiller for instead of a cooling tower, we're using water. This will be adiabatic, just a spray system, just to get, because Alberta is a very dry, warm summers. And then for the non-classified areas, we're going to be using chilled beams for the offices and that. And then the cage washers, and that is more of a, I guess, a setup for cleaning and preparing things. The fume hoods are what we call low flow. So they're about 0.3 meters per second. They basically have a fan system inside of them. Let me just go through my notes. I did miss the reverse osmosis for the water system. Now, the air handling unit is basically having 100% fresh air, and we have different weather, of course, than you guys do, so we have different problems. So at -30, we have what we call a summer filter here, and then we have a preheat, and that summer filter only stays in there for the summer when the weather is above 0 Celsius. When the weather goes below, we take that filter out, and we have a secondary filters here where this green part is, because what happens is we get a thing what we call hoarfrost, where warm, moist air participates out of the air and will come in, and it will freeze everything. So we need the preheat coil to melt that, or it will choke off the air from coming into the building. The next set of filters we use is a pre-filter, but we also have a MERV 14A, which is an E11 in Europe, ISO standard. And then the yellow block here is a special, what I call runaround loop, like Katia was speaking. And I'll get more into detail in the further slides, but this loop will do our heating, cooling, and energy recovering all in one coil, one heat exchanger system. And we're doing this because we're not too concerned right now at this stage with humidity control. Because if we have to dehumidify, we got to split the system out. And we do have reheats, electric reheats, like Demetrius did on his air control valves. The next stage is fans, and we use a fan wall system. So this system has roughly about 8 fans on the supply, and its end design is N+1. If one fan fails, the rest of the fans ramp up. The VFDs, we put a redundant VFD. So if one VFD fails, it automatically switches over to another VFD. And then we have our HEPA filters, what we call remote in the air handling unit. And then we're using a unique energy saving humidify system, which I'll speak into few slides down the road, and it's ultrasonic, which uses very little electricity. On the return air, we filter it again, and we're actually using a filter here to keep the coil clean. And again, a 6-fan array, and then exhausting out. We have approximately, I forget how big the building is, but we have about 110,000 liters per second for air handling units. This is that energy glycol system, the little schematic, and we can see that this is our summer temperature. So the air handling unit is bringing in the warm air, and then we're cooling it from the exhaust. So the return air is coming in, and then it's coming in at 23.9 degrees Celsius, and we cool it down to 25.2. And then we can see the loop here, how it gets fed. And we have two pumps here. One's redundant. And then what these are, and I'll show a picture later on, this would be a plate and frame heat exchanger to a boiler, and this is a plate and frame heat exchanger to a chiller. So we take that room air, cool it down just a bit. It's only 1.12 degrees Celsius, and then we cool it down with the chiller from 24.3 to 7.9 or 7.6, sorry, and bring it in to cool down the outside air a little bit from from 32C down to 12C, and then the electric reheats will take it from there. Typically these systems, because we vary the flow in the pumps, so we don't get laminar flow in the coils, we need turbulence at all time. The system, the coils, the heat exchangers are very high turbulence. The pumps on these things are about 200 to 300 kilopascals of head on it. Now here's our winter design. As we can see, coming in at minus 32, and this is where we get the bigger bang for our buck, because like I said, 6,000 hours in Calgary, we're in the heating mode. So our return air is at 22C. We cool it down to 5 degrees C, and that takes and heats it up, and now we got a heat exchanger from 15 to 32 to heat out the outside air. And we get about around 82% net efficiency. So that's subtracting the coil pressure drop and the pump energy on it. So the system we find is very effective when we need something that has no cross contamination and works well. The mean temperature in Calgary in our winter is about minus 12. So what we do with this system is we map every hour of the city for the whole year, and we find this is the mean temperature. So we actually design the coils and map the coils and the pumps for that mean temperature, not the extreme of minus 32 to plus 30, because when we get those two temperatures and we see when the most of the city, that's when we get most of our performance and savings. So we can see it's a much higher rate now that we're gaining before we're heating back up. And the one coil basically is doing our heating, cooling, and everything. So as the temperatures change, we can introduce the chilled water or the boiler water into these heat exchangers to fine tune the temperature. So we're always just controlling the loop and not directly of the coil. This is the skid with the two pumps, and this is the controls where the brains would be. And these would be all the control valves, and all the controls here would be going to each of the coils on the exhaust. And this could be the chilled water and then the heat exchanger as it needs to be added into there. The nice thing about it is this one skid can do so many different systems. And the next slide, I'll just show you how many systems we're doing. I think we have 5 or 6 air handling units on this project, and forgive me, I didn't change this over to metric. This is showing Fahrenheit and that, but I just wanted to show this, how many systems we can do on the one skid coming back, and then it can take the heat wherever it is in the building and put it where it's needed. So it's kind of cool doing multiple systems instead of direct. This is the ultrasonic humidification, because we're trying to achieve a net zero, and humidification in our territory is a huge cost because you're warming up the air, and then when you're humidifying, you're cooling the air, and our water is very hard here, and it's a very highly maintenance item to maintain. But with these new ultrasonic humidifiers, they only take like 2 amps of electricity, and they're just vibrating the water and misting. The bad thing about it is in our air handling units, we have to increase the absorption rate, so it absorbs very slowly. So the air handling unit actually gets quite a bit long in length. And this side, it's kind of a bad picture here, but this is just showing the steam it produces. And these are trays full of water in here that vibrate through, and the air flow comes up through here, and then it just mists. Again, the downside is the absorption rate. Humidification, I believe that's something in Greece you don't have to worry about, more of dehumidification. So we're trying to keep our carbon footprint down to the lowest, so we're using the best equipment we can find. And these are the new, what we call mag-bearing chillers. They're very quiet. There's no metal contact. The freon comes in, goes through a turbine and back out, and it just floats on magnets. They operate around 4,000 RPMs. They're very quiet, as you can see here, operating. This is a 400-ton chiller. We're using green gases, and our NPLV, which is adjusted for the normal operations and temperatures that we're using, because we're getting river water feeding into this system. And our COP calculation basically is a 10.1. This is the pharmacy part of the presentation, and we use, basically like Katia and Demetrius said earlier in their presentations, it's not much difference. You got terminal HEPAs. We don't use too many FFUs, fan-powered units. It's more attached right to the ductwork. And a lot of times we will put HEPAs in the air handling unit, feeding the terminal HEPAs. And the reason is that prevents these from loading up. So if they're not balanced perfectly even, or if some of them get damaged in the room, you don't create a balancing nightmare, because a lot of these pharmacies, once you breach this, they're shut down for quite a while through a cleaning phase. So that's typically what we do. We try to do very low flow at about 100 feet per minute through the filter, so they last a very long time. We do have alarm systems, pressure monitors across the rooms. This is just a display showing all the alarms and that, and I'll get on a little bit more detail further slides. And you can see the cascading pressures. The labs are ISO 7, so we got to have a minimum of 30 air changes, and with the alarm points, we do see that. Same thing with the pressure differential of 5 pascals across, and using terminal HEPAs at H14, which is our 99 point, shouldn't be a comma there, 99.995. The air pressurization system, using Venturi valves, controlling it, and we offset it from the supply. The unique thing we did on this job, we put door contactor, and this door contactor, what it does is when the door opens, the valve won't react to the supply or the exhaust, and that prevents a musical organ happening throughout the facility, because it only holds up for about 45 seconds, and once the door closes, if it doesn't close in 45 seconds, and then the valves will start alarming and trying to maintain pressurization. So this helps a lot of systems become stable. Other ways I used to do it in the past is just dwell back the controls so they're not so as sensitive to it. And also if two doors are open, we will have alarm systems so that we don't got pressure flowing down and creating some cross contamination. To save energy, we use this system quite often, and it's called it's sensing the supply air, and then it has room probes, and then we have exhaust probes and everything. And then what it does, it has a air router. So all these tubes are going to various rooms, and each air router has about 29 points. And it starts pulling air from each one, goes through a sensor bank. And these are robust filters that are there, and they are basically replaced every 6 months. So they're calibrated and tested, and we know that the system is always intact, so we don't have to do any separate testing of any probes or separate sensors. So the vacuum pulls it into this, and then from there we can display to computers, and then it will reduce the supply air, like to the Venturi valve in the room. For example, if an animal room is not being used, we don't need that 30 air changes or 15 air changes, or if that pharmacy is not being used on the weekend. The sensor will have a certain parameters of reducing that airflow from 30 air changes down maybe to, as we've taken them down as far as 2 air changes. So, we don't have to use that outside air, because when you're using 100% fresh air, that's a huge thing. And we're always sampling the outside air, because in our territory also we've had problems with forest fires the last few years. So if the outside air is not as good as the return air, we can actually loop the return air back in and have a system, what we call an emergency return. And we've done that in some hospital projects. Pharmaceuticals seem to stay away from that. I don't know if they're going to plan to shut it down, but we do have, the HEPA filters, and we're using an ionization system in this one to take out the smell. So I think we're just going to, because we have so much filtration, to take out the particulate and then use an ionization to take out the smell. We still feel that the air will be clean coming into the space. But we can use this system for humidity, temperature, VOCs, whatever contaminant we deem that is potential problem to the site, that we can filter it out. Lessons learned from all my projects, and it hasn't changed in 40 years, is always controls integrations and implementations are always an issue. Recently with the pharmacy lab, we had air balancing where our system has a certain reading on the Venturi valves, and then the air balancer comes with his instrument reading his. So we try to fine tune the two, because there's 2 different devices reading at 2 different points, and trying to get systems to read accurately. The other thing is seasonal testing, where we have winter and summer, making sure that both equipments are working, even on the solar seasons, that we need to tune things over and make sure. And I find one of the biggest problems is teaching maintenance, handover, and training them how to run the building, and usually sometimes overturning on personnel. You may train somebody, but and then they leave. Understanding the controls and making sure that the controls, for example, I had this last week where the building automation system says the outside air damper is open 50%, but when you actually went to the air handling unit, it was almost closed 90%. So it's double checking the controls with the equipment, they're tuned together. Well, thank you very much. If you have any questions or answers, I have my email there, and if anyone has any questions, I'd like to answer them.
Thank you, David. It was an excellent presentation. We'll have all the questions and maybe a short discussion at the end of the presentations.
Okay, thank you.
It was a great one. I would like to take all the credit for all the Dimitris you said, but really it is Stavros Livadas that he had to borrow my login credentials
Oh, okay.
have presentation. So we have to thank Stavros for all his work.